Come on in and don't be late. Let's learn science with Mr. Ed U Cate. G'day guys, in this video today we're going to be looking at chapter 3.7, buffer solutions, on page 92 of your textbook, Oxford textbook. But just before we begin, I just want to put this whole thing in context to make it a whole lot easier for you. All a buffer solution is made up of two chemical species that look basically the same. The only difference between this one here and this one here is the hydrogen ion attached to the acetic acid molecule. This one doesn't have the hydrogen ion. Remember, when you take a hydrogen ion away, the hydrogen ion having a positive charge, it leaves a negative charge to the molecule behind. So this is the acetate ion, acetate. And so that's one example. This is the acetic acid, acetate buffer solution, or buffer system you've often heard. Let's give another example here. Another common example is the ammonium and ammonia. Oh, sorry, no charge there. The ammonium ion, that's the ammonium ion, and that's the ammonia molecule. And that can exist in the aqueous form phase. So this is the ammonium, ammonia buffer solution. Okay, so in a moment I'll go back to the textbook, but essentially all the buffer solution is, in this first example here, is made up of two similar looking chemical species. This first one is actually a weak acid, and the second one is its conjugate. Remember from that last video, conjugate base. Okay, in this second example, this ammonium ion is another weak acid, and its conjugate base. Okay, so all the buffer solution is made up of a weak acid with its conjugate base, or a weak base with a conjugate acid. I probably should have given you another example showing you that, but I didn't want to confuse you too much. But just before we get started in the textbook, I just want to rewrite an equation that I'll show you from the textbook in a minute. It's this one here. It's a general equation for an acid-base equilibrium. So remember, in the last video, we talked about the idea that the acid and the base is on the left of the arrows, the acid and the base, and the conjugates are on the right. So which one is the acid over here? Okay, it's the one. They both have this one because they both have hydrogen. But the question you've got to ask yourself is, which one has the ionizable hydrogen, where the hydrogen ion can detach and go into solution? Well, it's this one here. This is a water molecule. The bonds are held together by covalent bonds, and it's pretty stable. So this is the base, and these two are the conjugates. Okay, this one is conjugate with that one, joined with that one, because they're related species. The only difference between this and that is that the hydronium ion contains an extra hydrogen. And so this is conjugate with this. Related species, the only difference is one has a hydrogen, another hydrogen ion. So this is the base and its conjugate acid, And this is the acid over here and its conjugate base. Okay, the A- ion. Okay, I hope that helps. Well, let's look at the textbook. Okay, so this is your textbook. We're on page, whatever it is. I think it's page 92. Yep, page 92. We're looking at section 3.7, buffer solutions. And the aim here in this section is how buffer solutions conjugate and resist a change in pH. And another aim is to predict a buffer solution's response to the addition of hydrogen ions and hydroxide ions. We'll go through some possible exam questions in a minute. But here's the general equilibrium equation here that I was showing you just a moment ago. And don't forget that HA, this one, is a weak acid, and A- is its conjugate base. And that's essentially what a buffer solution is. It's a solution that resists changes in pH when small quantities of acids or alkalis are added. So that's why it's important to set up your swimming pool with buffer solutions, so that, you know, when your pool undergoes a heavy day of use, it can resist those changes in pH. If your pool didn't have buffer chemicals in it, it would really, its pH would go up and down all the time. And we'll go through what those chemicals are in a little bit later in this video. But another example, apart from the pool, your own blood has a buffer system set up. The pH range of our blood is 7.35 to 7.45. This is a bit more basic than tap water and a bit more acidic compared to seawater. Tap water has a pH range of 6.5 to 8.5, and seawater is 7.5 to 8.4. So it's our blood is in between those pH ranges. If the pH is too low in our blood, the body suffers from acidosis, for obvious reasons. If it's too high, alkalosis. The blood becomes alkaline. In extreme cases, either of these conditions can lead to death. So the body maintains a safe pH level through buffer solutions, and the buffer solution that's in our blood is the carbonic acid. Where's that written down? Here we go. The bicarbonate and carbonic acid system. We'll look at that in a minute. But like any buffer solution, in our blood there's a weak acid and its conjugate base. Weak acid, conjugate base. So this system resists changes in pH in our blood. So how does this happen? How do buffer solutions resist a change in pH? Well, let's stick with blood. Our blood is maintained within the fairly short range. It's pretty close range for pH. So biology students will know what happens in the body. That magic word homeostasis. Homeostasis is achieved through this buffer system. This buffer system in our blood consists of carbonic acid as the weak acid. Carbonic acid, that's the formula for that, H2CO3, which is a pretty unstable molecule, but works really well in our blood, and its conjugate base bicarbonate, HCO3-. Conjugate base and weak acid. So, if for any reason your blood got too much acid in it, like you pigged out too majorly on sour worms or something, sour lollies, sour straps, this is what would happen. Okay, the H3O plus is the acid that enters into your blood, the hydronium ion. If that went up too high, that would combine with the bicarbonate ion, HCO3, hydrogen carbonate, or bicarbonate. And that's an equilibrium with the carbonic acid molecule and a water molecule. So this is the reaction that occurs if your blood increased to too much in acidity. If a small amount of base was added to the blood, the base reacts with the carbonic acid this time. The base, hydroxide ions, reacts with the carbonic acid, H2CO3, and that produces, or is in equilibrium with, the bicarbonate ion and water. So these two reactions, this one and this one, control the pH of the blood by removing excess hydronium and hydroxide ions. So it depends what enters the blood. Too much hydrogen ions, we call upon the base. The acid that enters the blood reacts with the base, the conjugate base, to balance out those excess hydronium ions. But if too many hydroxide ions enter the blood, it reacts with the acid, the weak acid. Okay? It's pretty simple. So a lot of this relates to our old mate, this guy. And I just reminded myself what the correct pronunciation of that was. Now let me teach you. It's not Le Chatelier. That's a dodgy way of saying it. The proper way of pronouncing this French name is Le Chatelier. Le Chatelier. Le Chatelier. So get practicing on that one. So Le Chatelier's principle relates to buffer solutions. And here we go. This is the equilibrium system in our blood. We'll stick with the blood. It's what's the word for it? It's concurrent, I guess you could call it, because there's more than one double arrow. There's a double arrow here, double arrow here. So this whole system is the buffer solution in your blood. If your blood gets too acidic, in other words, if there's a process that occurs in your body that produces more hydrogen ions, the hydrogen ions are over here to the right of the equation. What happens is, according to what is it again? Le Chatelier's principle. If you've got excess hydrogen ions in the blood, this will push the equilibrium to the left, because the hydrogen ions are over here in the equilibrium. You get too many hydrogen ions, it'll push the equilibrium to the left. If another process produces too much base, hydroxide ions, now there's no hydroxide ions showing here in this equation, but there's hydrogen ions. If too many hydroxide ions build up in the blood, the equilibrium will shift to the right to produce hydrogen ions to neutralize those hydroxide ions. Okay? So just read about it again in your textbook just to go over it. It's pretty straightforward. I'll draw another one for you in a minute. But in the meantime, here's another case study. The pH of shampoo and how manufacturers control the pH of shampoo. Shampoo is actually acidic. It sounds bad, but a slightly acidic shampoo smooths down the scales on your hair follicles and flattens them out, so as it were, and makes your hair look smooth and shiny. If you washed your hair like I did as a kid, I cut corners. I don't know about you. I was a bit dodgy as a kid, and I washed my hair with soap. That's a bad thing because it makes the scales on your hair not flat, makes them stand up, makes your hair look frizzy and dodgy. But how does this work? Well, the manufacturers just add a buffer solution, and you know what a buffer solution is now. It's made up of a weak acid and its conjugate base. So shampoos contain the conjugate base such as sodium citrate. The weak acid is actually not citric acid. So weak acid, citric acid, and its conjugate base, the citrate ion in the form of sodium citrate. Okay. Hope you're taking it in so far. I'll just give you one more example in a second. So let's try to solve a problem that you could come across in an exam. Here we go. I've gotten this out of another textbook. Write equations to show what happens when acid is added to the following buffers. And I've given, we'll work on two problems here. The acetic acid acetate buffer and the ammonium ion ammonia buffer. So let's work on the first part first, hey? All right. Part A. The acetic acid acetate buffer. Because acetic acid is actually a weak acid, remember, if we're dealing with a weak acid or a weak base, it's in equilibrium with the products. So we will have a go at this. I'm going to write down the formula for acetic acid as this. CH3OOH. We could write it down as C2 H4 O, of course. That's its empirical formula. Oh, sorry, O2. But I'd like you to get in the habit of writing acetic acid down like this. We're about to start in Unit 4, Organic Chemistry. And the formula for acetic acid, acetic acid in organic chemistry, if you had to write down the structural formula for acetic acid, it's this. The structural formula, that's the structure of the molecule, the acetic acid molecule. C2, there's your two carbons, H4, 1, 2, 3, 4, 1, 2, 3, 4, and two oxygens, these two. So you can see why we write it like this, because this carbon here is attached to 3 hydrogens, CH3, and this carbon here is attached to 2 oxygens and a hydrogen at the end. So that's the reason why I'm writing it like this for this question. Acetic acid, when you add it to water, will make an equilibrium with the acetate ion. That's just the same molecule but without the hydrogen, the acetate ion, and H3O+. Again, like we looked at the other day, this here is the acetic acid molecule is the acid. Water molecule acts as a base. It acts as a base because, remember, it accepts protons, accepts the hydrogen ion. Bases are substances that accept a hydrogen ion. And these two must be the conjugates. Conjugate, too lazy to write the whole word. Conjugate, well, we'll start with this one. Conjugate acid, this one, because the hydronium ion is an acid, is the acid particle. It's got an ionizable hydrogen ion, and this must be the conjugate base. The acid is connected to the conjugate base, and the base is connected to the conjugate acid. Just to double check, this molecule here was this one before it lost a proton. This one, the hydronium ion, was the water molecule before it gained that extra proton, hydrogen ion. Okay, so have we answered the question? Write equations to show what happens when acid is added. We've written the equation, but we haven't actually answered the question. So we've got this buffer solution system set up. If you added more acid, more hydronium ion, H3O+, the equilibrium would shift to the left. Le Chatelier's principle says that if you stress a system, in this case add more acid, the system will shift in a direction that will use up the added stress, will shift in a direction that relieves the stress. You add more of this hydronium ion, the equilibrium will shift in a direction to use up that hydronium ion. So it shifts to the left to produce more acid and acid molecule, acetic acid molecule and base. Okay, so that's question A done quickly. Let's move on to part B, ammonium ion and the ammonia buffer. We looked at this before, but just quickly again. The ammonium ion. Remember, a lot of these polyatomic ions formulae are in your data book, so it takes a stress out of remembering them. But it's good to try to remember them. Remembering these molecules actually helps you to understand them better. So the ammonium ion added to water, mixed with water to make a solution, that is, produces the ammonia molecule and H3O+. This is the acid because it's got an ionizable hydrogen ion. This is the base because it accepts that hydrogen ion. This is the conjugate base. Ammonia is a well-known base. Conjugate base and conjugate acid. And so they're the conjugate pair. The ammonium ion, the ammonia ion is a conjugate pair, and this is another conjugate pair, the water and the hydronium ion. So what happens if this system here, I'll just put that over there, put something to cover it up. There we go, something to cover it up. What happens if you add more acid? The exact same thing as before. Add more acid, would shift the equilibrium to the left to use up the hydronium ions. Likewise, if you added a base, it would shift to the right this time, would shift to the right to produce more acid molecules to neutralise that base. So there you go. That's the end of this video. Hope I kept you engaged there. Look, just email me at any stage in trying some of these check your learning questions that are on page 93 of your textbook. In trying some of these, just send me an email if you have any troubles. Stay safe and be good.